Okay, write small. I always start out by writing the formula. When you have more than one term in something, you'll want to subtract, because you're subtracting f of x, that means you're subtracting all of it. So I'll put a set of brackets around the whole thing, because one of the first mistakes you may have made is you subtracted the 2x but forgot to subtract the 4x. Of course, this is all over h. Now, x plus h times x plus h times x plus h. I'm going to multiply two of them first. I'm going to distribute that 4. You see that here the x squared plus 2xh plus h squared, that's just me doing x plus h times x plus h. I still would have to multiply by another x plus h. Just to save me a little bit of time, I see that those minus 4x's cancel out. You're going to, this example in particular, really, really, really appreciate the shortcut when we learn it. So here we're going to go 2. When I multiply this x plus h through again, I'm going to get x cubed plus 3x squared h plus 3x h squared plus h cubed. You might have to do that off this side and draw all the arrows and combine your like terms. That's okay. We still have plus 4h minus 2x cubed. This 2 is going to get distributed to each thing. I hope you can see that those things will cancel out. But you would still have that 2 distribute to every single one. So I will have 6x squared h plus 6xh squared plus 2h cubed plus 4h all over h. Factoring out the h, leaves me with 6x squared plus 6xh plus 2h squared plus 4. And now my h's go away. And when you plug in 0, where the h's are, you are just left with 6x squared plus 4. Do you need me to scroll up? How? Any questions about any lines? Because I did take some shortcuts, like when I multiplied this to get this, I did take a shortcut for that. Are you aware of how to do that with distributing the x to everything, the h to everything, and then combining your like terms? Ooh, does anyone know what shortcut I used? Not quite. Sum of cubes would be like for factoring stuff, right? I'll tell you in a bit. Can I scroll down to here? Is that? I heard the word triangle. That's part of the. I didn't hear the. I did. Some kind of triangle they called it. That's the one. Yes. Pascal's triangle. That was the shortcut that I used. Once we're done copying this, I'll go to Pascal's triangle and show it to you again, or show it to you for the first time, and you can see how I used it in this case. What's that? How I got this highlighted part. I could have done that directly, but I did the steps that most likely you would do. But I could go directly from x plus h cubed to that answer. And I'll show it to you after. So the shortcut that I used for going from this to this in one step is something called Pascal's triangle. Pascal's triangle is famous in a lot of ways. Pascal's triangle looks like this. Now that I've showed you 5 rows, can you tell me what the next row is? It's going to start with a good pattern recognition. The next one's going to be 5. The first 2 are always the easiest. The next one is 10. How do you get 10? 4 plus 6. You could just add the 2 above it. That'll work. Or if you're in Canada and want to use the hockey stick identity, you just draw a hockey stick, and all the numbers in the shaft of the stick, 1 plus 2 plus 3 plus 4, will equal the number at the toe of the stick. I don't know if the hockey stick identity is officially what it's called, but since we're in Canada and it looks like a hockey stick, if it was Christmas, I might call it the Christmas stocking identity. And that works for any number as you go along, as long as the shaft goes all the way to the end. Say 1 plus 3 plus 6 will equal 10 for that one as well. Okay, some things about this and the way that it relates to x plus h cubed is that row there. Anytime you have something cubed, you'll have 4 terms. The 1, 3, 3, 1 become the coefficients of the expansion. And the exponents, you're going to have a variable of an x and a variable of h. You're going to start with all of your x's, x cubed, and slowly decrease until you have none left. And h, you'll start with none of them and slowly increase until you get to h cubed. So that is how Pascal's triangle is related to the binomial theorem and binomial expansion. Pascal's triangle also has tons of other cool things. Anybody know any other cool things in Pascal's triangle? If you add up the numbers in each row, you get the powers of 2. That's pretty cool. Not super cool, but pretty cool. If, oh, now I'm getting off topic. Are you okay? Okay. With Pascal's triangle, if you just look at them as numbers, 1, wow, that's yellow. 111, 121, 1,331. These are the powers of 11. This is 11 squared. This is 11 cubed. 14,641 is 11 to the power 4. How do you work with tens? Well, you just have to sort of carry numbers over, and that's 11 to the power 5. You see how I did that with that row? Started here, 1, 5. This will be a 0. The 1 will come over, get 11. The 11 will carry over to get a 6 and then a 1. and that's 11 to the power 5. You can check on your calculator if you don't believe me. So there's the powers of 11. Very cool in Pascal's triangle. Also, if I had written my triangle very nicely spaced out, which it sort of seems like the edge of the board kind of made it squished here at the end, but if I had done a very pretty triangle, and you happen to choose, say, a line with this slope, you take that line with that slope and slowly move it through Pascal's triangle. You hit a 1. Then you hit another 1. Then you hit 2 1s, which adds up to 2. Then you hit a 1 and a 2, which adds up to 3. Then you hit a 1, a 3, and a 1, which adds up to 5. Then you're going to hit a 1, a 4, and a 3, which adds up to 8. What's happening? Do you recognize those numbers? Those are the Fibonacci numbers. If you haven't ever heard of the Fibonacci numbers, go to the library, type in Fibonacci numbers, and there's numerous volumes of books written about the Fibonacci numbers. Very fascinating things. How do you find the next Fibonacci numbers if you know the other Fibonacci numbers? What's the pattern? The next one's 13. What's the next one? 21. Next one? 34. How do you find them? You add the 2 previous ones, and then you get the Fibonacci numbers. I could talk about those for another hour, but we're talking about Pascal's triangle and not the Fibonacci numbers. There's Pascal's triangle. Also, if you kept making Pascal's triangle bigger and bigger and bigger and bigger, and every time you ran into an even number, you shaded it in. Maybe you took out a crayon, because you can. Let's do black crayon. And every time you hit an even number, you shaded it in. There'll be another even number there. And you made a very, very big triangle of Pascal's triangle and looked for a pattern in the triangle. You would get Sierpinski's triangle. How many people have heard of Sierpinski? Sierpinski's triangle here. I'll find a picture of it for you. Ooh, how do you spell Sierpinski is another good question. Sierpinski's triangle. That's how you spell it, not the way I was. And there's some images of Sierpinski's triangle, which is a fractal of a triangle inside of a triangle inside of a triangle inside of a triangle. And all of the shaded parts would come up with this. That's Sierpinski's triangle. Some very cool things.